Welcome to the second morning session. We'll continue with highlights from Quark and EDM. And it's our great pleasure to introduce to you to Sneha Malde from Oxford that will give the experimental overview.
So, good morning. So I'd like to talk to you about quark flavor physics. And so the motivations that we have for studying this is to understand the weak force in the quark sector, to look for the CP violation, and then to try and constrain the UT triangle to find new physics sources that might be there. We want to look at rare decays and have a look at their enhancements that could come about due to new physics. And then we can also search for charged lepton flavor violation, or essentially decays that are not allowed within the standard model. There's an experimental niggle in all of this, which is that quarks aren't free. They come in bound states, which adds complexity to the standard model prediction or its interpretation of the data. However, one thing we do have is experimental diversity. So I've put the logos of some of the experiments that are covered in this talk. Each of these is very unique. They have different particle species that they can access. Some were designed for this type of physics. Some were designed with a more general purpose in mind. They are competitive in specific places, but for the most part, we have complementarity. And it's by bringing all of this information together that we can make a good understanding of quark flavor. Sometimes this type of physics can feel incremental, as I tell you about one branching fraction after another, and there are many of these. However, if we take a look at the progress over the lifespan of one experiment, which is LHCb phase 1, we see that we have understood much more about the CKM angle, the CKM matrix. We've understood more about rare decays and QCD. Flavor physics sets the scale on new physics. And what I want to do in this talk is to use the recent results to show where we are today, and also the types of measurements that we are already doing that will set the scene for our future. I want to start off with one of the most simplest decays, which is a DS meson decaying to a lepton and a neutrino, in this case a muon. It's an example of how QCD and the weak force are intertwined in these decays. This branching fraction measurement can be measured very well at BEST3. This is a E plus E minus collider, and it's a hermetic detector, which allows for constraints that mean actually inferring the presence of that neutrino becomes quite easy. So this is BEST3 makes the most precise branching fraction, and from that we can interpret the CKM element. But we do need to input our knowledge on form factors. Another place where BEST3 is quite unique is that it is the only big source of charm mesons that are produced in a quantum correlated state at the psi double prime. So the difference in these two plots only happens because there is the quantum entanglement. We can use this as a source of interference, and therefore exploit this to make determinations of the parameters of the strong phase, and this is actually a key input into CP violation measurements at LHCb and BEL2. So one place where these measurements have been used heavily are in measurements of the CKM angle gamma. So this is measured in tree-like, in tree beta decay-like decays. What's neat about gamma is that we can actually access all of these hadronic parameters from the data itself, as long as we have these inputs on the charm side coming from the charm factory. The lack of QCD input means that it's one of the most pristine observables in flavor physics. We're accessing fully hadronic decays, which means that we need kaon and pion separation, and therefore LHCb and BEL2 are very good places to do this. At BEL2, the focus has been on beta decay decays, which is essentially the golden channel, the one from which ultimately one gains the most sensitivity. Many different D decays are used, I've shown here D to K short pi 0, which is a channel yet to be accessed at LHCb. What you see is essentially a measurement of direct CP violation. So essentially, you want to know how many B pluses there were compared to how many B minuses. We only expect about a 10% asymmetry in this particular channel. So with the data given, it's not quite easy to see, although you can see that there's a little bit more on the left-hand side than the right. On LHCb, having sort of almost fully exploited the B to DK channel, we look at B0 decays, we look at states of the B plus with excited kaons and excited charm mesons. I've picked one of the new results here, which is B to DK star plus. And here the asymmetry was expected to be about 60 or 70%, so you can see that actually with a very similar event yield, you have a much larger asymmetry. At LHCb, we can also access BS decays, which is time-dependent analysis. We reach a tagging power of 6.1%, which allows us to tell whether we have a BS or a BS bar. And this is the asymmetry as a function of time. And the fact that you can see the difference between the red and the blue curve is a sign of the CP violation. So because there are many measurements here, you want to make combinations. And so there are... at Bell, the combination has reached about 7 degrees. At LHCb, we're at 3. And so what we can do is we can compare this to the indirect prediction that comes from the rest of the UT triangle, which is about 66. So as we see right now, we have consistency between these two determinations of gamma, and it will take some effort to drive the precision down further to try and look for further discrepancies. Another measurement of the CKM angle, the CKM triangle, is beta, which is measured in B0 to J psi K short decays. This is decay time-dependent CP violation of B0 and B0 bar decays. The observables are the direct CP violation and then the mixing-induced CP asymmetries. Wanted to show this plot from LHCb, which beautifully shows the capabilities of the detector in looking for this type of CP violation. An updated result on the same channel from Bell. Here there have been significant improvements to the flavor tagging algorithm, which is based on graph neural networks, and the tagging power reached is about 37%. However, in these decays, it's the tree amplitude that's dominant. But other beta SQQ bar decays have larger penguin contributions. And this is where we might be sensitive to new physics if they were to play a part in the virtual loop. So we want to make measurements of CP violation in a range of B decays, some which would have larger penguin contributions, to have a further understanding of what these are and what they contribute to the standard model part, but also to search for the effect of new physics. So progress here. So from Bell 2, there's a measurement of CP violation in B to J psi pi 0. It's the first observation in this channel. And this channel can really be used to constrain the penguin contribution that would occur in J psi K short, the previous measurement. There's also measurements in B0 to eta prime K short. Now here you actually expect that this diagram, that this decay would be penguin dominated, and so you're looking for deviations. As you can see though, one needs to have a lot more data to be able to really probe this at the level we want. On LHCb, we've been looking at BS to K short HH decays, and this allows us to refine the QCD prediction from these branching fractions for these and other charmless modes. We can do a similar study in BS decays. Here, the angle is actually very small, and the prediction is small, but new physics can cause enhancement to the mixing part of the diagram. It's a slightly more complicated analysis because you have to disentangle CP even and CP odd amplitudes and also deal with the non-zero width difference of the two BS eigenstates. The recent measurements here come from LHCb and CMS, with the CMS having a larger tagging power at 5.6% using cutting-edge techniques. It's a competitive measurement, and it's actually the first evidence of CP violation in this channel. However, as you can see from these three measurements, that there is some discrepancy on the width difference. However, at LHCb, we can access a large number of BS decays in the light and heavy states and make direct measurements of delta gamma S which happen to be consistent with the standard model. So as these measurements become more precise, the understanding of the penguin amplitudes will become more important. I move now to CP violation in the charm sector, which is fairly new, and it's the only CP violation we have in the up sector. The standard model predictions, however, are very difficult because of the long-range effects, so essentially the hadronic stuff. And CP violation is actually expected to be very small, so at around the 10 to the minus 3 to 10 to the minus 4, not the 10 to 70% I've been talking about before. So to date, we've only seen single-mode evidence in D0 to pi decay, so we want to search elsewhere. So here's a result from LHCb that's recent, and because it's a three-body decay, we can look for local CP violation in the phase space, which is expected to change because as the phases change. The signal yield here is an astonishing 135 million events. However, the data, unfortunately, is consistent with CP symmetry, so we simply need to keep searching longer and harder. Another channel is D0 to K short. Here, both diagrams have similar contributions but different phases, so maybe in this channel, CP violation is a bit larger. There's a recent measurement here from CMS, which comes from a dedicated data set, which is used to collect data for heavy flavor physics, enhancing the experiment's capabilities in this type of work. The results are consistent with CP asymmetry, however, and a little bit less precise than what we've been seeing at LHCb. One place we haven't observed a CP violation but expect to is in the interference of decay and mixing. So here the golden channel could be right sign to wrong sign D to K pi decays, where we can look at this ratio as a function of time. From this analysis, we did make significant improvements in the mixing parameters, but there was no evidence of any CP violation. But you can see that the contours have shrunk, and hopefully we will eventually edge out that no CPV point. Let me move now to flavor-changing neutral currents, which are suppressed in the standard model, but can be enhanced by new physics. Beta SLL transitions have a consistent pattern of the rate being too low in certain regions across many channels, so they've been a source of strong interest. One of the golden channels here is B0 to K star mu mu, where we study the differential branching fraction as a function of 3 angles and Q squared. So to reduce the dependence on the hadronic uncertainties, it's written in terms of optimized observables. P5 prime is only one of these, but it's the one I'm going to focus on today. There's a new result from CMS, and so what you can take away from this plot is, first of all, that the data lie above the standard model prediction, that the results are of comparable sensitivity to the ones that exist from LHCb, and most importantly, it confirms this discrepancy between the standard model and the data. In order to try and interpret these results, we use an effective field theory here, where we have effective couplings instead of the loop diagram. We can do global fits of all the branching fractions, and what we see is that in the C9 Wilson coefficient, there is a significant discrepancy with the standard model value. So is this new physics, or is this simply a lack of our understanding of the hadronic effects? To try and counter this, we do a full amplitude analysis at LHCb, which takes into account the light hadron resonances, charmonia, and also double charm loops, so DD bar, D star D, and also the tau loops. The interpretation of the results from this analysis is that there probably is some contribution of non-local amplitudes that leaks into the binned analysis that wasn't previously accounted for. However, there is still a preference for a result for C9 that is shifted away from the standard model value. We should also look at different flavor-changing neutral currents, and a very interesting one is B to K nu nu bar. Here, the prediction is more precise because we don't have these additional hadronic uncertainties that come beyond form factors, unlike in the beta SLL transitions. But we have instead a very challenging signature. So this requires a full reconstruction of the event and the tag side, and there's a new tagging method at Bell 2. And this has allowed for the first the first evidence of this decay, and interestingly, the branching fraction sits above the standard model prediction. Kaon physics remains very relevant today as well. It can constrain the UT on its own. And a similar decay is K long to pi 0 nu bar in terms of a flavour-changing neutral current. What's been going on here is that with these very rare decays, you want to keep the background as low as possible, so the detector has had new hardware that allows some of the charged K on background to be removed. And overall, the background is decreased by a factor of 5. No events are seen within the signal region, and a branching fraction is set. At NA62, which measures the counterpart K plus to pi plus nu bar, there is new hardware, and analysis of that data is well underway. The last one I'd like to talk about is D0 to mu mu. This has an incredibly small branching fraction, where the long-distance effects are dominant. But it's a very interesting decay because it's the only one in the up sector, and it's basically used as a building block of new physics models. A new result from CMS here, using their new data and their new trigger, sets the best limits at 2.6 times 10 to the minus 9. Let me move now to lepton flavor violation, which is forbidden in the standard model. So if there are hints of non-universality in decays that include B to C L nu bar, then it's likely that we might be able to see decays like this. And there are other things that point to the same thing, and it's expected that the couplings to the third generation quarks might be the largest, and in this decay both B and tau are present. To overcome the missing neutrino, there are constraints set on the direction and mass of the phi and the tau. No signal is seen. There's B to K short tau lepton is searched for at Bell 2 and Bell with a similar motivation, and this allows, and here they can compute the recoil mass of the tau lepton, which suppresses background. But again, we still don't see a signal here. So what I've been saying is essentially that we do want more data to be able to do more studies, more in-depth studies, to take CP violation measurements further. But the good thing is that even as I speak, we are collecting more data. So at LHCb, we've just undergone a substantial upgrade, which increases the data taking rate and also the hadronic trigger efficiency. An ambitious further upgrade is planned for the 2030s. At Bell 2, there are also improvement plans for the interaction region and the detector, which would allow for data taking at a much higher rate. The best 3 charm dataset has recently increased by a factor of 7, and we should expect to see results from that filtering through very soon. There are plans for a super tau charm factory. A lot of the other experiments that I have mentioned are taking data at the moment, and some also have upgrade plans. So to conclude, there is no obligation for new physics discovery to be easy, but what we have done is we've shown that we can do the really complicated things. So this includes multi-body decays, time dependence, flavor tagging, amplitude analysis, and these really challenging final states. We've also shown that we can maximize our current data through cutting-edge techniques, and we can push experiments beyond their design. And we also exploit the synergies that can exist between experiments to build our knowledge together. What we know is that interpreting the results from across the board of quark flavor is going to require a better understanding of things like the penguin amplitudes, form factors, and hadronic uncertainties. But what I have shown today is that we're already making these measurements that will help us understand these things. We've got some very powerful data sets that are on their way, so I think this is a very exciting way to understand the standard model and to search for new physics. And I think we've got a very exciting future ahead of us. Thank you.
Thank you very much, Sneha, for this really comprehensive and nice overview. Are there questions? Please.
So a comment as a retired flavor physicist and then a question. So if you go to the beginning of your talk when you had the 2010-2024 comparison, so you said that you see there the impact of, let's say, LHCb1. Not sure I agree. So what I see there is the progress with lattice QCD. And particularly the fact that once the quenching error was gone, the treatment of the lattice errors by CKM filter became similar to the one of UTFit. Because in 2010 and 2004, they were differing in the fact that effectively CKM filter was linearly summing the quenching error from everything to everything else, while UTFit was doing a convolution. So if you look at the 2010 UTFit plot, it looks much more like the bottom one. So the striking impact in the utility triangle analysis, I think, is a bit more on the lattice than on experimental front. Of course, the impressive shrinking in gamma is there. But if you look at the precision of eta and phi, and in eta and rho versus time, which is in Marcella's talk of Friday, you see that it's pretty much flat.
So, yes, there is a lot of QCD input into both of these plots. But as you said, gamma has improved, I think, almost by an order of magnitude, a little bit more than that. Also, much more precise measurements of BS mixing constrain this, and also it's these inputs that go into the...
No, the measurement of the mixing doesn't impact. What shrinks the bands is the lattice input. If you look at the measurement, basically it's a delta function. The moment you measure it with such a precision, which is way better than the theory, that you are completely dominated by the theory uncertainty.
But we have measurements of lifetime and branching fractions, and all of these feed into the QCD and how they build, how they build what they're going to do on the lattice. And measurements of our spectroscopy have also gone into that. So I think it's not a one or the other. I think both experiment and theory are required.
Now, the other question I have, when you refer to the phi s versus delta gamma plot, and you talked about inconsistency between the tension between the measurements, I think you said. I honestly don't see it. I see three measurements which are overlapping each other within one sigma.
It's not significant, I'll give you that, but we should try and understand this further, and there are ways to do that.
I can give you 35 of those plots between others and CMS.
Should we maybe take that question into the coffee break? Are there other questions? Please.
Yeah, thank you for this very nice overview. You showed also an outlook, which I find very nice, how the field will progress, or at least how much new data will arrive. You didn't really say what this will bring in terms of understanding flavor physics, the new, the big questions. But anyway, after these very exciting new data comes for the next 20 years, if in 20 years we have a new machine which increases the Z, which was very important for flavor physics, of course, when we had lab. Now we have the prospect of having 1 million times more events on the Z. So what makes us excited about that in terms of flavor physics? What will this bring to the table after we have all this data?
So I think there are some very specific places where that data set at the Z resonance can bring us. So I think particularly in terms of things that involve a tau lepton, which, as we've seen, could be quite interesting. And I think that physics would do very well at such a collider. And I think we can make good measurements of everything else, but I think there's quite a lot of studies still going on to see if... I don't think we should wait for such a factory, is what I'm saying. I think we need to have progress in the next 20 years, and then we should be able to figure out what our next set of measurements would be. But there are certain capabilities in a detector, for example, at FCCEE, especially with things like tau leptons, that I think would be better than maybe LHCb upgrade 2. But as we've seen, these experiments have a way of excelling themselves. So.
Okay, then I think we need to move on. Let's thank the speaker again.
And we continue now with Toru Iijima, who is going to report on Lepton flavor physics and EDM.
Okay, thank you for invitation. So I represent on the Lepton flavor physics and EDM. So here is the outline of my talk. I talk on the muon G-2 and muon charge Lepton flavor violation programs, and then tau physics at level 2. I apologize that my talk cannot cover or is very brief for EDM dedicated measurements, which is very interesting, in fact, and also cannot cover Lepton flavor violation in meson decays because of the limited time and also because of my limited ability. There is no indication of new physics beyond the standard model at LHC. Flavor physics experiments play important roles in such a situation. In fact, there are a few anomalies often discussed in the community. One is the muon G- anomaly, where the recent Fermi-Lab result deviate from the standard model reference value at the level of 5 sigma. Another case is a B anomaly, so-called, and where the most quoted example is a test of Lepton flavor universality test in the B semi-Lepton decay, where the ratio of the B to D over D star tau u over to the electron or muon final state, the ratio has a deviation from the standard model more than 3 sigma when the worldwide data is combined. So Lepton seems to be a key probe to search for beyond the standard model physics. Charged Lepton flavor violation is almost background-free from the standard model. So if it is found, it's a clear signature of a BSM. EDM is a CP violating observable, so it probes the new source of CP violation at high energy scale, which could be relevant to the baryon asymmetry in the universe. Both have sensitivities to the very high energy scale, maybe 10 to 3 TeV or 10 to 7 TeV, as shown in this figure. On the other hand, G-2 is a flavor diagonal observable, so if deviation is confirmed, then it may indicate a mass scale of unknown particles. So it is very important. So let me start with muon G-2. Experimentally, it can be obtained by precisely measuring the spin precession frequency with respect to the cyclotron frequency, as shown in this equation. There has been a long history in step-by-step improvement, test the quantum correction by first QED, hadronic, and electroweak, by a gradual improvement of the experimental sensitivity. When the Brookhaven experiment achieves a precision by which we can probe electroweak contribution, then it found a deviation from the standard model at a 3 sigma level. What was interesting is that the size of the deviation was similar to the size of electroweak contribution that may indicate the new physics scale is somewhere similar to the electroweak scale. So that was very much intriguing. So that's why we still have this effort. And in this decade, we have an experiment at Fermi-Lab and also at JPAC. In the experiment at Fermi-Lab, so-called magic momentum is used so that this second term is canceled out, while that JPAC experiment uses a so-called ultra-cold muon beam, as I explained later. Muon G-2 experiment at Fermi-Lab use the same G-2 ring moved from Brookhaven and target statistical uncertainty of 100 parts per billion with 20 times more muon measured. And also 100 parts per billion total systematic uncertainty to measure the mu with 4-fold improved precision of 140 parts per billion. Such a small systematic uncertainty is achieved not only by carefully measuring the G-T frequency, but also very precisely measure the magnetic field with accurate field mapping and field tracking, and that is weighted by the actual muon distribution extracted by trackers. The experiment achieved already the goal statistics and completed, and so far the data up to run 3 have been analyzed, and the result have been announced last year, as probably most of you know. In the recent runs, by better control of temperature, magnetic field stability, and also pile-up corrections, and so on, the systematic uncertainty was already reduced to 70 parts per billion. That is better than the design. The final result using all data is expected to come sometime next year. That's what I heard. The experiment has also a sensitivity to EDM at the level of 10 to minus 21 by searching for up and down asymmetry out of the phase with omega A, which is 1 or 2 orders of magnitude better than the Brookhaven measurement. On the other hand, muon G-2 EDM experiment at JPark used a completely different approach, which is a unique independent measurement of G-2 to test BNL FNAR result with different systematic uncertainty. In this experiment, surface muons are brought to rest in the muonium production target made of silica air gel. And then the produced muonium was laser ionized to make an ultra-cold mu+. Then it is reaccelerated by 4th stage of linear accelerator system, as shown in this figure, with a low emittance muon beam produced so that they can storage in without no strong focusing and good injection efficiency to the compact storage magnet, where that magnetic field uniformity can be easier controlled. The construction is starting gradually, aiming at data taking from 2028. The expected sensitivity after 2-year running is, in statistics, 450 parts per billion, which is subject for improvement later, and then, but systematic uncertainty of 70 parts per billion, which is similar size to the Fermi-Lab measurement. EDM sensitivity is also at the level of 10 to minus 22 to 20 minus 21. The team recently achieved the world-first acceleration of positive muon. And so such a muon cooling and reacceleration scheme was verified using the setup shown in this picture at the JPark facility. You can see a clear signal of accelerated cold muon coinciding with the laser turned on in this time of flight spectrum. And we also measured the profile of the accelerated muon beam. So this is a great milestone achieved for the future G-2 measurement, also for other applications, for example, to the muon microscopes. So, while such an effort, experimental effort are in progress, we also have to work on further for the reference standard model prediction. Currently, hadronic vacuum polarization, HVP, is a dominant error source, which is very difficult to calculate analytically. So there are 2 approaches taken. One is so-called dispersive approach, data-driven, and E plus E minus data used to estimate the quantum correction, hadronic quantum correction. This is the approach actually taken by the Theory Initiative white paper in the 2020 K20. Another approach is a lattice approach to calculate this contribution by large-scale computing. And recent calculation like a BMW20 achieved comparable error and gives prediction closer to experiment. Another approach may be come by mu-on-E experiment under preparation at CERN, which provide a new independent evaluation by a mu-E to mu-E differential cross-section measurement. There are two issues. One is a difference between this dispersive approach and the lattice approach, and the latter gives a result closer to the experiment. And the second issue is attention within this dispersive approach, where we have about 3 sigma difference between Barbara and Chloe data. And more recently, CMD3 gave a very large number, which deviate at 2 sigma or 5 sigma with respect to Barbara or Chloe result. Okay. So this slide shows new result from CMD3 at the BEP 2000 E plus E minus collider in Novosibirsk, where they scan the center of mass energy in this range. And this plot shows there are results which are the statistical precision a few times better than the other experiment. And the cross-section gives the cross-section higher by 2 to 5%, as you can see clearly. They also have a subset, very nice subset result, where they measure the forward-back charge asymmetry, by which they can better understand the angular distribution so that better determine the fiduciary volume. And this is also an important input for the better radiative correction modeling, as shown in this figure, where the data is compared to some radiative correction models. Babar also measured additional radiations in E plus E minus processes, and the result indicates the contribution of higher order radiative processes, NLO with 2 gamma or NLO with 3 gamma are significant, and pointed out that ISR measurement, if Monte Carlo generator does not correctly account this contribution, if so, they are effective. As shown in this figure, where the 2 Monte Carlo generator are limited to NLO and include both NLO and NLO are compared in the ratio of data Monte Carlo comparison. So radiative correction need to be better understood and accounted in analysis. In such a situation, new data from a new experiment is welcome and important. And E plus E minus correction measurement with the ISR method is in progress at BEL2 also. They released the first result for E plus E minus 3 pion final state with 2.2% error, where the uncertainty arises from the Monte Carlo generator, which missed the NNLO contribution. So the results are about 2 sigma higher than Babar and global fit, as typically shown in the bottom figure, shown here. And our next goal is to measure the pi-pi final state with target precision of 0.5%, although it takes a time. In any case, BEL2 has joined this important community-wide activity, so please stay tuned. There is a news coming to this conference by the BMW collaboration, which achieved 40% reduction of uncertainty with respect to compared to the previous version by final lattice size, and also include a small but long-distance contribution obtained using input from the E plus E minus data, where they all agree. So this red point is a new result, and this compared to the older one, and the central value get closer to the experiment, and the difference is now 0.9 sigma. But of course, it's not the end of the story, and we need to clarify the situation of other lattice, And also we need clarification of the difference between E plus E minus and lattice and also tau-based data. So as one of the organizing committee, I advertise a coming theory initiative workshop at KEK in September. And that will be the workshop before releasing the next version of theory initiative recommended number. So there will be so this workshop will be this is a workshop for a very hot discussion, and maybe with very cheap Japanese yen. So you are welcome to attend. And the registration deadline extended to the end of this month. Now I come to lepton flavor violation muon decays, and for mu gamma, MEG2 is now running and targeting the sensitivity of 6 times 10 to minus 14. And at the PSI, also mu2 3E experiment is under preparation, targeting this sensitivity, and also further by upgraded accelerator. MEG2 released the first result last year using the data taken in 2021, where no excess event observed above the background, but nevertheless, combined with the old MEG result, the most stringent limit to date is obtained. Next release using 2020 data is coming soon, and MEG2 will continue data taking till PSI accelerator shutdown in 2027 to achieve this goal. This slide shows a status of mu2E conversion at JPAC and Fermilab. Both experiments target sensitivity of around 10 to the minus 15 in the last decade of this, in the last half of this decade. And then that push down the sensitivity by 2 orders of magnitude with full equipment in the next decade. And you can see how the preparation is in progress. At JPAC, there is also a DME experiment, and which has a sensitivity of 10 to minus 13, and which may start earlier than COMET was a JPAC. COMET was a mu2E. Now I come to the tau physics at BEL2 at supercake V, which plan to accumulate 15% band of E plus E minus collision data, which provide a large sample of tau decays. Tau is the heaviest charged lepton, sensitive to the beyond the standard model physics. And lepton flavor violation search with the tau is complementary to the search with the muon. To push down the sensitivity or precision, it's not only the accelerator luminosity, but also there are many technical challenges on the detector side, typically improved particle resolution, particle ID, and so on, and also the improvement in the analysis technique based on machine learning. BEL2 accumulated more than 500 inverse band data, and we released several results using the data set taken by before summer 2022. This is a result for the test of lepton flavor universality in tau decays, where we compare the tau leptonic decay to muon final state to electron final state. And this is a deduced coupling constant ratio from this ratio. And so this is the most precise test of E mu universality in tau decays from a single measurement, which is consistent with the standard prediction at the level of 1.4 sigma. This is also a new result for the tau to 3 muon from BEL2. And the BEL2 analysis explores also the 3-pronged decay for the tag side to improve the efficiency while keeping the background low enough with a better background rejection using BDT. So BEL2 already obtained the world-best limit, although the data size is about half of the previous BEL experiment. Okay, because of the limited time, I skipped this, but some new result also obtained for the tau to lepton plus vector mesons. So tau physics, so this compiles the results so far obtained by the various decay channel of tau, and from several experiments. And Bell 2 will push the sensitivity down to 10 to minus 9 at 5 inverse autobahn, and then minus 10th with a 50 inverse autobahn data. Tau EDM recently constrained by the new updated Bell measurement at the level of 10 to minus 18, and that will be further pushed down by at the Bell 2 experiment. And there will be an opportunity also at the LHC, higher LHC, and also propose the future facility like a super tau charm, FCCEE, and CEPC. Okay, I have only one slide for the worldwide effort for the EDM. And there is an effort for the electron, EDM, muon, neutron, and more, including proton. And I cannot explain each of them, but maybe I should note that new bound by the half-new molecule measurement at the GILA Institute has this limit, which is very much intriguing because the mass scale, it's interpreted as a mass scale for a new CP version source could be higher than the 40 dB. So I come to the summary. And because I ran out of time, I don't read all of these. But none of these projects are not easy, but many challenges are in progress. And so for those people working on this project, ganbarimashou in Japanese. And the interesting result will come in 2025 and 2030. So please stay tuned. Thank you very much.
Thank you, Toru, for this interesting and comprehensive overview. Do we have questions or comments? There is one on the left side from my point of view.
So regarding G-2, there's all these discrepancies in the E plus E minus data, and I've had some pessimistic statements about the willingness of the experimental collaborations to go back and look at the data again and try and understand why the data is in tension. Could you comment on this possibly?
Well, there are many details, so I cannot explain fully. But this contribution of higher the process is something pointed out recently. And so experiment use a different Monte Carlo generator and so on. And so ideally, it could be uniformly treated. And but whether it can be done for the old measurement or not is an issue that I don't know. Yeah.
Okay, it would be great if they could go back and reanalyze this data and find out.
Yeah, we need a discussion at the workshop.
Yeah. Okay, thank you.
Are there further questions or comments?
Okay.
So oh, there's one, sorry, please.
Thank you for a very informative, very comprehensive talk. Also on G-2, are there any other collaborations beyond BMW that are using some different way of calculating these effects so that the systematic uncertainty in these calculations can be washed away in some sense? It's always unclear how to interpret that error bar in the lattice calculations. Are there any other collaborations coming up?
Honestly speaking, I'm not a lattice expert, so I cannot answer. Maybe some.
Well, maybe I'm able to give a comment. There are several lattice calculations ongoing at this point, different groups using different fermion discretizations, different sets of gauge fields. Some are quite orthogonal from the setup to what BMW has been using. And so far, they have split the contribution which is most critical to be calculated on the lattice, and that has been done by several groups, and they are in excellent agreement, all with comparable errors. And the full window, or the full calculation for G-2 has not been completed by another calculation at this point. Their BMW is the only one, but I think at least 2 other collaborations are close to completing the full calculation, and eventually already next week at the Lattice conference in Liverpool, you may hear updates. Do we have another question or comment?
Yes, thank you. With this plot just showing, so could you just say maybe where this new Bell 2 result would lie on this plot right there?
New Bell 2 result is not included here because Bell 2 measured just only for 3 pi final state at this moment, which is not the leading final state is a pi. So yeah, it's not included yet. But in future, when we complete the pi result, yeah, we of course hope that we have a plot here from the belt. Yes.
Okay, we have another question on the right. The last one, please.
Okay. A brief question. I mean, it was so nice to see a discrepancy between theory and standard model theory and experimental results for once.
Yeah, sure.
If that also goes away, where does this leave us? I mean, does that mean we push the boundary of scale of new physics into the multi-10 TeV range? Does that give us any hope to see anything new ever in the next 20, 30 years?
Well, I'm an experimentalist, so what I can say is that we should work on this establishing this G-2 measurement, and well, how I can answer your question. But for such a high energy scale, maybe I just show one slide, but this recent electron EDM result seems to be intriguing, and it's quite sensitive to the energy scale, higher than the few 10 TeV. Of course, it depends on how this coupling constant is, but if you take a typical number, then it looks, intriguing.
I think we can follow up on that question with the next talk, but now let us thank Toru again for his talk. Thank you.
Then we continue with the last speaker, Alakabha Datta from the University of Mississippi, who is kindly filling in for Zoltan Ligeti, who's very sorry that he cannot be here.
Okay, thank you to the organizer for asking me to give the talk. Now, if you have seen a version of the older version of the program, this talk was supposed to be given by Zoltan Ligeti, but he had an accident. So I'm the emergency replacement here, so I didn't have much time to prepare for the talks, but Zoltan was kind enough to share some of his slides with me, so I'm going to use those slides. And the organizer asked me to start with say something about the 50 years of charm discovery. So most of the material here is material that Zoltan had prepared. And of course, we had some excellent parallel session talks. So I'm going to use them in this presentation. So I will start with the 50 years of charm discovery, then start the flavor physics part, so testing the flavor structure of the standard model, which is the UT fit. So we already saw some of this in the parallel session and also in the talks before. I'll talk about the anomalies, because that's something that everyone is kind of interested in, what's going on. And then, kind of motivated by neutrino masses and mixing, I will look at some interesting directions in flavor physics. Of course, we heard about charged lepton flavor violation, but also I will talk about signatures of stellar neutrino This is again motivated by the discovery of, or the evidence of B plus to K plus invisible, and also talk a little bit about how we can explore dark sector in rare decays to invisible states, again, in like K to pi invisible or B to K pi invisible. Okay, so here is the JSI discovery. It's 1974. It's kind of the November revolution observed by 2 experiments at SLAC and BNL, the Spear accelerator here and the AGS. And this led to a big flurry of discoveries in both in theory and experiment, discovery of new particles and development in theory. Soon after, 2 weeks later, the D meson was, the psi prime was discovered, and then the D meson, the psi and psi prime are hidden charm states, so CC bar states, where the D is an open charm state. Now, there was also evidence of charm already in some cosmic ray, in some cosmic rays by groups observed by groups in Japan. Okay. So here is the evidence of this particle X going to pi plus pi 0. And of course, associated with this is the ICHEP mechanism. And that was the theory based on 4 basic quarks. And this was trying to explain why certain flavor-changing decays like K long to me plus me minus is highly suppressed. And normally you would expect S to D tree-level flavor-changing transition. But this is not there because of in the 4-quark picture, where there is a cancellation because of the unitarity of the mixing matrix. And so this ICHEP mechanism actually required that the charm quark should exist. Okay. So this was followed, of course, by the Kobayashi-Masukawa paper about trying to incorporate CP violation. If you have only 2 families, you can rotate away the phase in the mixing matrix. So you had to go through at least 3 generations, and you're left with 1 phase, and which pretty much explains all the CP violation that we have seen so far. Okay. So what's the big deal here? So it's the ICHEP mechanism. It was 1970. There was the proposal for the KM matrix in 1973. And based on that, there were some important papers here, one by Guyard and Lee, where from the delta MK and the K long to me plus me minus, you could actually estimate the mass of the charm quark, which is about what we know it is to be today. Okay, so here are some comments actually by Zoltan. So since 1970, flavor has been an input, a very important input to model building. Since strong constraints on TV scale neophysics have been known. We all know that how flavor-changing neutral currents play a very important role in constraining any extension of the standard model. And so this kind of, any model you write, you always have to check that you do not have unacceptably large flavor-changing neutral current effects. Okay. So, so here is kind of the, okay. So let's go to, start with the UT fits. There was a paper, there was a talk by Sony, who actually emphasized the importance of this unitary triangle fits. There are important progress in lattice on epsilon prime. And there was also implication for the K-on unitary triangle, which are based on the rare K-on decay. So here's the CKM fit here. And this was a fit which is by the UT collaboration here. So what we are trying to do is to actually construct this unitary triangle here. In the standard model, this triangle should close. And we try to extract these parameters here. Eta is the imaginary part in the CKM matrix here. So in this Wolfenstein parametrization, There is the phase which live in the VTD part of the unitarity triangle and the VUB. The VTD, you're measuring through the angle beta, and the VUB through the angle gamma. And so we are trying to kind of constrain this and try to see if its angle closes. One of the important things to mention here is that a lot of very impressive experiment and theory has gone into constructing this triangle here, because from the theory side, we always have to deal with hadronic uncertainties, right? We have to talk about, and we heard a little bit about this in the first talk, we have to worry about penguin pollution, how it affects the extraction of these parameters. And one of the things that you can do to check the standard model is also compare. For instance, if you look at the angle gamma, you can measure it through processes involving 3 processes, but you can always compare it with angles that you can, for instance, the same angle gamma that you can get out of penguin-dominated processes like B2K pi or BS2 K plus K minus. And so it's interesting to see the gamma that you get from those decays, penguin-dominated decays, where you expect new physics to be present, and compared it with the extraction of these parameters from tree-level processes. OK, so again, the scale of new physics, as I mentioned, that if you take just general flavor structure here, from the measurements that we've already made, the scale of new physics can be very high. So if there is new physics, which is supposed to be at a TeV scale, the flavor structure cannot be any generic. It has to be, there has to be more structure in the flavor, in the flavor sector to actually get a new physics if it's around a TeV. But for a generic flavor structure, the scale of new physics is pushed to be very high. And it's pushed the highest from probably the K decays, the K mixing. OK, so let's go to the B anomalies here. So there are the 2 charge current and the neutral current anomalies. The charge current is just in the semi-Leptonic decay of V to D star tau, and you're comparing with V to D mu and electron. And it's a very simple process. It's a tree-level process. The only hadronic uncertainty comes from this matrix element here. And this is a heavy transition. And the form factors have been studied since the 1990s, where we have been using the heavy quark effective theory here. So we are looking at these 2 ratios. And in the standard model, because the W boson couples equally to all generation, we can actually predict this. And we can test for the Lepton universality here. And this is the product that we have seen a lot. And so there is now about a 3.3 sigma deviation from the standard model. So what do we need to do here? First, we heard a lot of interesting talks in the parallel session about new developments in the form factor, which will refine the standard model prediction for this decays. And then you can also see if there is new physics, then given the measurement in this decay, what can you tell about the structure of new physics? And there was a nice talk on like a flavor, a model-dependent talk by Svetlana with leptoquarks, and then there was a model-independent discussion here. Okay. Let's go to the neutral current here. So the neutral current anomalies are in the B2S mu here, and it goes and it's described in the standard model by this Wilson's coefficient C9 and C10, and the C9 is associated with this operator here, where the lepton interaction is vector-like, and the C10 where it's an axial vector here. Okay, and then connected to this are the B2S nu and also the B2S gamma here. Okay, so here are the plots from the talks here, and this is a kind of cute way to explain what the situation is. So what we are seeing here, and this we are seeing for a long time, is that if you look at the branching ratio of the decays, for instance, like B2K star LL or B2 phi LL, the predictions of the standard model based on your input from form factors is always less. I mean, the measurement is always less than what is predicted by the standard model here. So the predictions are less than that. And then we also saw deviations in the P5. And then the best way to test for new physics is actually to compare the ratio of B2, the so-called RK ratios, where you actually look at the ratio of B2K mu mu and say, or B2S mu mu over B2 SEE. The nice thing about this is that while these two measurements are not exactly theoretically clean, there are hadronic uncertainties here. This is a very good test of new physics because a lot of the hadronic uncertainties cancel. There is a little sensitivity to the lepton masses through radiative correction, but to a very good approximation, we want it to be 1. Okay. Now, that was kind of about 2 years ago. The situation was that, we seem to be seeing a deviation in this ratio RK star, and there was a lot of excitement for a long time because this, if true, would be a really smoking gun signal for new physics. Okay. Of course, the situation has changed now. While these discrepancies still remain, the lepton flavor universality ratio test of that is now consistent with 1. So what is the situation? The situation is that given that these discrepancies still remain, there can still be some new physics, but the fact that these ratios are now close to 1, it implies that if there is new physics, it has to be lepton universal new physics, or it is some underestimated QCD effects. Okay? So what are the QCD effects here? It's very simple. Here, basically, you can have non-leptonic operators. So here is a charm loop. And so you have 4 quark operators, and then through an exchange of a gamma, then it can go to L plus L minus, and because this coupling is universal, so you get equal contribution to muons and electrons. Okay. And so we heard about a talk on how we can actually experimentally try to fit these various contributions, which are coming from single exchange or a double exchange of these systems. And then there is a contribution which is taken from a possible contribution from B to S tau tau. Okay? Now this is very interesting because if there is new physics, the current way to explain this lepton universal new physics is to have some new physics in B to S tau tau, and then through this tau tau loop, you get an equal contribution to muon and electrons. Okay? Now, because the contribution to muon and electron is same now, it's actually difficult to have a model where you have a leptoquark which is coupling equally to muons and electrons, because you will generally generate mu to E gamma at a very unacceptable rate. So the way to handle this is instead have like a BS tau tau operator, and then you can actually, through running, generate equal contribution to muon and electrons. Okay? So here was the fit. Here is where you actually include this fit to this long distribution contribution. And the significance is lowered. It's about 1.5 or 2.1. On the other hand, if you use some kind of known methods or accepted methods people have been using to estimate this charm background, then you get a significance of about 4 sigma. Okay. So let's look at the kind of operators that you can use to generate this B2S mu mu and EE effects. And here are the operators written for SMEFT. The Q's and the L's are the doublets, and the E's and D's are the singlets here. Okay? And many of you will realize that these two combinations, 1 and 3, LQ1 and 3, were studied a lot, because if you look at the LQ3, there is this, it's a triplet. So in principle, this can also contribute, if you actually look at these two operators, you can have a joint explanation of the charge current and the neutral current anomalies, because you get a contribution from here, which can explain the RD star. Okay. So what you can now do, so these are the list of semi-leptonic operators that can potentially generate a C9 at MB. And here are the values that you need. So these numbers are written in terms of a Wilson coefficient over TeV squared, and this is what you get. But it's also interesting that you can also look at 4-quark operators. And there are a whole bunch of 4-quark operators that one can write down, and you can ask if those 4-quark operators, through their running, can also produce the same effect in muon electron. Okay. And it turns out that you can have actually a few of them here in red, which satisfy all the constraints. You have to satisfy constraints from BS mixing, epsilon, epsilon prime, and also the phase of the B sub S mixing, which is measured from B sub S to J psi phi. What is interesting about 4-quark operators is that now you get contribution to the gluonic penguins. And so now you will not only have effects in B2SLL and B2S, but you'll also have effects in B2SQQ. So you can actually look at effects in all the penguin-dominated decays in non-leptonic B decays. So there can be a correlation between the semi-lepton anomalies and some anomalies in the hadronic sector. For instance, there is an old B2 pi k puzzle where it's difficult to understand the CP asymmetry of, between two modes. And so there can be a nice connection between this hadronic penguin and also semi-leptonic penguin. OK. Going to lepton flavor violation, again, moving to the second part of my talk. The lepton flavor is conserved in the standard model. Neutrino oscillation implies that there is lepton flavor violation. And you may observe in charged lepton flavor violation. We already heard about this in the previous talk. And again, instead of looking at models, one can actually, this is a nice slide from Julian, which was presented in the Beach conference. So you can actually look at all possible effective operators that you can write at dimension 6. And it turns out that there are 888 operators. So a lot of time to work with this. And based on taking each operator at a time, you can actually see what kind of decays you are generating. So you generate decays like Z to mu U, E, mu to E, and so on. And these are the limits for a generic structure of order 1. This is the scale of new physics that you're exploring. Okay? And so this is the one which is current, and then in the light region, this is the range that you can get in the future. Okay. So as you can see, you can actually explore the scale of new physics to very high scales. And you can do it with the different terms in this effective Hamiltonian, and so on. So there are all this kind of decays, and you can put bonds on that. Now, if you are more adventurous, and if you want to have even lepton number or baryon number violation, you add 564 more operators, and then and you can kind of play this game. You can allow for some cancellation and look for some interesting signals. Okay. So let's go now to one of the other motivations for neutrino physics is that maybe there are sterile neutrinos, right? And typically, when you look at sterile neutrinos, you look at their effects through the sterile neutrino mixing with the active neutrino. But that's not the only way the sterile neutrino can interact with the standard model. In fact, whenever you write new interactions, there are new interactions involving the sterile neutrino. It can be through the Higgs, like left-right symmetric models, or even leptoquarks. Many of the leptoquarks models that we have been studying for the anomalies actually also has a coupling to a heavy right-handed lepton, but we usually neglect them. Right? So we can actually study these also in an effective theory in which we have included the sterile neutrino or the heavy right-handed neutrino as an explicit degree of freedom. And so this is called the new SMEFT or SMNEFT. Okay? So you can write a whole bunch of operators here, which are in addition to the operators that you get in standard model effective field theory. Okay. So now you can look at some very, very interesting signals here. One, obviously, is just the production of this right-handed neutrinos through various meson decays. And here I'm just looking at B decays. So now if you're actually parametrizing new physics, now you have two possible structures on the leptonic sectors. You can have left-handed and right-handed currents. And in fact, the fact that these new operators could solve the RDR D star puzzle was actually proposed a long time ago. Okay? So, but you can actually do better. Even if the rates come back to the standard model, in this decay, you have got enough statistics that you can actually reconstruct the full angular distribution here. So you have got a B goes to D star, goes to D pi, and on the other side, you have the lepton and the X, which can be the sterile neutron here. And all this vertex information is included in this function here. Okay? So what are the signals you can look? At least in BEL2, one of the simplest signal you can look for is just look at the missing energy. So if there is indeed, so you expect in the standard model the missing energy to peak around 0 here. But if there is also a sterile neutrino contribution, then you can see a shoulder here. So that's something that we are actually working with some BEL people at Hawaii and Melbourne to actually develop the signal Monte Carlo for this. But you can also look at the angular distribution. For instance, you can look at the Q-square distribution and various other angular distribution, and there are some unique signatures of this heavy right-handed neutrino here. Okay. It's interesting that the same processes can also be explored at other experiments, which we usually associate, for instance, like collider experiments like phasor, because the process in which the sterile neutrino is produced is exactly what you're doing at BEL2 or LHCb. And in this case, again, through effective operators, you can actually look at the decay of this of the sterile neutrino. And you can actually, depending on what kind of operators are producing this decay, you can actually, by looking at, for instance, if you look at the neutrino decaying into E plus E minus nu, by looking at the opening angle, we can actually see, actually, potentially be able to say a difference between a Majorana and a Dirac neutrino. OK. Let's go to B2K nu very quickly. Again, we heard that there was the evidence of the first evidence of B2K plus nu. The nice thing, unlike B2KLL, is that it is there is this, the long distance contributions are no longer present, so it's theoretically clean, experimentally very challenging, and it seems to have a 2.7 sigma. So this is something that we should look out for. So again, many ways to do it. Again, focusing on sterile neutrinos, you can kind of write down operators here, which can explain. So here are two sterile neutrino operators you can have with one neutrino active and one sterile neutrino, which can actually kind of explain this. Okay. Another signature of another interesting interpretation is that what you're actually seeing is, because you're looking at invisible decays, you're looking at B plus to K plus invisible, it could be a light state. Okay? So there was a nice talk here in which there are many suggestions of light states. So this was kind of generalized all possibilities, including all possible light states here. One of the disadvantages of the ephetic operator is that you lose correlation between different sectors. One of the things that we would really want to see is that if this process stays B plus to K plus invisible state, are there any implications for the K plus to pi plus invisible, which are being explored by, say, NA62, or in the Koto experiment for K long to pi 0 nu bar. Okay. So very quickly, there is a simple model in the next 2 minutes. It's basically a dark Higgs, which actually mixes with the Higgs sector, and it actually produces, and then this dark Higgs then couples to the fermions through this mixing, and then a sterile neutrino is also included here, so that the dark Higgs can also couple to the sterile neutrino. So what happens here is that in most of this kind of dark Higgs sector, they are produced through the flavor-changing neutral currents here. So they are produced through the B2K KS and then the K to pi S. And while the B2KS is dominated by the top penguin, for the kaon, you have to also include the charm contribution, which is important. Anyway, there can be some interesting effects in neutrino physics. Because the same setup actually explains, might explain some of the excess event, mini-boon events, but I don't have time to go for it. But there are some interesting predictions. So again, what one should look out for is that if the B2K plus individual stands, the focus goes into the rare kaon decays. Okay. So anyway, I'll come to the conclusion. So the standard model continues to be tested in flavor experiments. There are interesting anomalies, more data, and theoretical improvement needed. There are many decays which can be sensitive to dark sector like sterile neutron and dark Higgs. And the future with more data is kind of exciting and will definitely improve our sensitivity to BSM physics. Thank you.
Yeah, thank you very much for the very comprehensive overview. You covered many things.
Right.
Questions, please.
Yeah.
Thanks. Maybe it's more of a comment, and maybe it's more of just to address a question we had earlier. That you know, we sometimes hear, like in the last few talks, that we have this new scale of physics. That it seems like we have all these measurements that say that there's no sort of flavor violating physics or no new physics below 40 TeV or 100 TeV.
Yeah.
But I guess what I wanted to point out is that maybe for the young people also, just to give them a bit of hope, that I think you know, if we make some simple, well-motivated assumptions like new physics only couples to third generation,
right.
Is strongly coupled to third generation, and you know, not so much in the first and second.
Yeah.
All of these constraints, everything we have says that you know, this mass scale is, you know, maybe above 1.5 TeV, which is very accessible, something that we can do in the high luminosity LHC. And if we were to get something like FCCEE, we can go a factor of 10 higher by doing these precision electroweak and flavor measurements. So I just kind of wanted to point out, just to give people a bit of hope that we do have really a future of finding new physics in the next few years and in the future.
I hope so. I share your hope. Yeah, absolutely. Yeah.
Do we have more questions here?
I mean, it's along the same lines as what Ben just said. I mean, also in the discussion of the anomalous magnetic moment that we had just before. I mean, if one just, they have obviously, because of this apparent discrepancy, there have been a lot of theoretical papers written trying to explain such a deviation in some type of new physics model. And if you look into these papers, normally the new physics that does the job is relatively light. So we're not talking about models with the 10 to 50 to 40 TeV scale, but this is new physics that is relatively light, sometimes in the 200, 300 GeV scale. So it's not that everything points us to things that have to be so heavy.
Absolutely. Yeah, I agree. Yeah, sure.
Do we have more questions? Here. Over there.
It is more as a comment. So in celebration of 50 years since November Revolution of 1974, both SLAC and BNL will have special public events. They are on our laboratory's website, so, and we welcome everyone to come.
Okay, thank you. Yeah, sure.
Could you go back to when you were showing that the ratio of the e to the mu finally came out to be 1, but those other anomalies apparently are still around. Here.
Yeah.
So what made the? Do you have any idea why the one on the right came back into? I mean, what was changed to bring the one on the right?
That's a LHCb experimental problem. I mean, so that they got their systematics correct, and so.
It was a question of systematics.
I think so. There are more people. Yeah.
Thank you. I was wondering if we were going to get that question. So over there you have 4 bins corresponding to 2 decay modes. What you have in mind is probably a result that we had around 2020, where indeed we had a tension with respect to the standard model, when there was the analysis that took into account all of these bins together, we profited from the knowledge of the simultaneous fit to make sure that we understood all of the backgrounds. So long story short is that part of the reason why there was that tension with respect to the standard model is that there were some backgrounds which were not accounted for as well as should have been the case. Once this is done, you see that now all of this is kind of nicely compatible with the standard model.
Thank you, Yasmin, for commenting. Do we have more questions? Looks like we're all satisfied. Thank you again very much for the talks, and let's thank all the speakers, and this closes the session, I guess.